In the beginning, there was information. A presentation written and narrated by Chuck Missler and Dr. Stephen Meyer.
It's interesting when you study the Apostle Paul, being a Pharisee of the Pharisees and so forth, that when he went into a synagogue, he would always preach from the authority of the Scripture and his role as an apostle and so forth. But when he went to Mars Hill in chapter 17 in Athens, very interesting, he preached from their frame of reference. He discovered that among all the idols, there was one called the unknown God, and he used that as a springboard, speaking in Greek terms. He was very educated in the Greek term. You know, one of the problems we have as we try to witness is too often we try to impose our biblical platitudes on those that don't have that background as a common frame of reference. And one of the mythologies that pervades our entire culture is this whole thing that we call the evolution debate. And what we really mean by that isn't evolution in the broader sense, but in the sense of biogenesis, the origin of life. Because to us, with a biblical point of view, we take for granted so much because we have discovered that the Bible is really the Word of God, and we start with Genesis 1 and go from there. Failing to recognize that the culture we're in hasn't yet discovered what the Bible is really all about, and so forth. Now, there is a breath of fresh air crossing our land in the halls of science. In fact, the great tragedy is that this breath of fresh air in science has yet to find its way to our high school and college campuses, because the textbooks and so forth are still full of the mythology and the false evidence that's now been disproven. But there is a raging debate in the scientific world, and what's refreshing is that this debate is being shifted to where it belongs, because the debate isn't between creation versus evolution. That's falling into their trap. The great discovery is that biogenesis is bad science. And one of the things that, if you read in this area at all, you'll discover there's some shining lights. William Dembski and Michael Behe, and also one of the names you'll see in the important papers is Dr. Stephen Meyer. And one of the things that I'm delighted to be able to do tonight is to divert from our usual schedule and have Steve make some presentations from the field of science, from the field of all the sciences, biology. Dr. Stephen Meyer is director of the Center of Renewal of Science and Culture of the Discovery Institute, which is headquartered in Seattle. He's the associate professor of philosophy at Whitworth College. He did his doctoral work in history and philosophy of science at Cambridge University in England. His dissertation was on the origin of life, the origin of life question. Prior to his academic background, he came from a signal processing background, so he has a grasp of a relatively new science, as sciences go, the information sciences. And that's why it's so close to my heart, and so much that of what I've used, I've learned from him. And it's just a delight to be able to have him share with us tonight using some of his background and some clever aids and so forth. I'd like to introduce to you Steve Meyer. Steve?
I do have some clever aids tonight, some toys, in fact. One of my favorite students at Whitworth confessed to me one time that she was a science loser. And I think a lot of people suffer from a kind of science phobia. And so I've learned in making these presentations that often it helps to use some colorful visual aids, and I'll introduce them at the right time. I've also found that in making talks to scientific audiences, that using visual aids can often be very helpful. That the Darwinist mythology that we're engaged in fighting, I think traffics in obfuscation, that is to say, making things unclear. And if you can make things clear with a visual aid or with an illustration. Even the scientists seem to appreciate that, and it tends to help our side in the argument as you cut through all the academic jargon. So if you're feeling a science loser tonight, take heart. We'll try to bring this right down to a level that both people in the liberal arts and the sciences and working people can all understand. Last summer there was a movie, I guess maybe it was 2 summers ago now, by Carl Sagan. Some of you may know of the name Carl Sagan. He's the famous astronomer who died a few years ago. He did a series called Cosmos on PBS, and he was famous for, he's a guy that said that talked about the billions and billions of years, And at one point, he said that the universe is all there is, and all there ever was, and all there ever will be. And that is the credo. It sounds a little bit like almost the Christian credo, the Gloria Patri, It's an anti-credo. It's the credo of the materialist or the naturalist. In philosophy, we talk about people who are theists, that is, people who believe that there is a God beyond the physical universe, and there are people who are naturalists who believe that the physical universe is all there is. And Carl Sagan was an advocate of that naturalistic worldview. And so it may be a little surprising for me to start my talk tonight with an illustration from Carl Sagan, but even our naturalist colleagues with whom we disagree capture some important parts of the truth. And in the movie Contact a couple summers ago, Sagan was able to convey something that I think is very important. Could we have the first slide? There we go. This is a radio telescope pointed to the heavens, and it says, "As I read it, we're receiving a message from outer space telling us to stop bombarding them with unintelligible messages." Some of you may have heard of the search for extraterrestrial intelligence, and Carl Sagan had a fictional movie and book based on this called Contact. And in it, there's an important truth. As the story goes, there's a young lady scientist who's been manning the radio telescopes looking for evidence of extraterrestrial intelligence. And one day, coming across her console, she gets a series of zeros and ones that suddenly attract her attention. And the zeros and ones are coming in the standard binary code. But suddenly she realizes that what she's looking at is the sequence of the first 100 prime numbers, a kind of universal mathematical language. And she gets very excited, and the story is based on the premise of this scientist discovering evidence of extraterrestrial intelligence. Now, Sagan takes the movie in some interesting directions, and in the end it becomes quite mystical and pantheistic. But what's interesting about this is the recognition, even by a staunch naturalist, that there's a connection between intelligence and information. Most of us know that from our ordinary experience. If you encounter a hieroglyphic inscription or a cave painting or even a billboard or a sign, and there's information on it, you immediately infer that there was an intelligence behind it. And that's part of our common sense knowledge, because we know that only intelligences can and do produce information. So Carl Sagan, this staunch atheistic naturalist, I think has a very important insight. And we're going to build on that in the talk tonight as we look at the information that's actually present in life. The next slide, though, illustrates that we didn't actually need Carl Sagan to tell us this. You can illustrate, we often explain things by reference to the actions of intelligences. And sometimes we explain things by reference to unintelligent causes. What Sagan illustrated was that it references, explaining some things like the prime number sequence or something would be a legitimate way to explain things by reference to intelligence. But let me illustrate 3 ways that we explain things ordinarily. We have a fellow here named, I guess it's Joe, yeah. And his pacemaker battery has quit. And imagine you're a forensic scientist and you're trying to figure out what caused this pacemaker to quit. You've got a couple options, actually 3. The first would be that the pacemaker just quit by chance. The story on this one goes like this. The pacemaker's battery, though expected to be fully functional for at least 5 years, happened by chance to run out after only 1 year. When the battery ran out unexpectedly, Joe's heart fibrillated and he died. Okay, that's the explanation. It's a chance, referring the explanation of Joe's death to chance. Next kind of explanation, though, different kind. The pacemaker's battery, though guaranteed to be fully functional for at least 5 years, was sure to run out after 7 years. Joe was negligent. He refused to replace the battery. When the battery ran out after 7 years, Joe's heart fibrillated, and he died. Okay, in this case, we call this necessity. This was built into the laws of physics and chemistry that the battery could no way last longer than 5 years. He failed to change it, and so as a matter of necessity, not of chance, he died. Now, the third mode of explanation is the one that we're going to be very interested in tonight, and that's called design. And this is a malevolent form of design in this example, but it's design nonetheless. Joe was murdered. Joe's enemy exposed Joe to significant amounts of microwave radiation, or maybe he was told to turn his pacemaker off, not to interfere with the videotaping. Anyway, it was an intentional act, all right? So Joe died because his enemy exposed him to significant amounts of radiation. He was murdered, and this caused the pacemaker to stop functioning. When he did, Joe's heart fibrillated, and again, he died. So you've got the same event with three possible explanations. One that refers the event to chance, one to necessity, and by that we usually mean something like the laws of physics and chemistry, and the third is by reference to design, by reference to an intentional act of an intelligent agent. When we look at those, when Carl Sagan's fictional scientist looked at those signals coming in from space, she inferred that there was an intelligent cause. That was a design inference. She was inferring that intelligence was behind that information on her console. The interesting issue when we begin to talk about the origin of life is whether or not there is any evidence of design in life. For the last 150 years or so, most biologists have assumed that there is no such evidence. Darwin's theory, in fact, was said to be a theory that explained away the appearance of design without actually invoking a real designer. The mechanism of natural selection acting on random variation was said to be sufficient to explain the appearance of design in living organisms without actually needing a real designer. So natural selection functioned as a kind of designer substitute. It was, in fact, by reference to these categories, a combination of chance and necessity together. Okay? So it was a purely naturalistic explanation for the appearance of design in organisms. Now notice I keep saying that organisms or animals look as if they were designed. Almost all biologists agree to that animals look as though they were designed by an intelligence. In fact, the arch-Darwinist Richard Dawkins says that biology is the study of complex things that look as though they were designed for a purpose. He says, of course, we know they weren't. The blind watchmaker, he calls it, of natural selection, does all the real work of designing, and so God didn't have anything to do with it. But everyone in biology agrees that biological organisms, animals, cells, give the appearance of design. They're very sophisticated. And what we're going to ask tonight is whether or not that is a sufficient explanation or not. Most of us know that that Darwin's theory attempted to explain where complex living things like elephants and human beings and birds and reptiles, how complex animals like that came from simpler animals. And Darwin's theory of biological evolution attempts to explain precisely that, where the whole range of the animal world came from a very simple starting point. He said one or very few simple forms. So this is the idea of amoeba to man evolution, starting from a simple cell and working your way up. Now, it might surprise you, but I'm going to set that question aside tonight because, in a way, for the important question of design, it's somewhat irrelevant. I think there's evidence of design in complex animals, but the startling discovery of the last 50 years of the 20th century is that the very simplest thing, the thing that Darwin thought you could kind of concede as a given, the simplest living cell, has turned out to be enormously complex. More complex than our most advanced supercomputers, more complex than a Boeing 747 airplane, more complex than all this audio-visual equipment that we're using tonight. So the Darwinian scheme was if you start simple and allow natural selection to do its work on random chance variations, and you give it enough time, you can build enormously complex things starting from something very simple. But the problem with that whole scheme is that starting in the 1950s, scientists began to realize that the very simplest thing was not simple at all. It was extremely complex. And that undermined another theory, a companion theory to Darwin's. It was not the theory of biological evolution, moving from simple life to complex life, but the theory of chemical evolution, which sought to explain how you went from simple chemicals to the first life in the first place. And I've got on the screen a schematic of that theory. The idea here is that, apologies to those who may not be able to make this out. I'll try to describe it with words as best I can. The idea of chemical evolution was the idea that if you had some simple atmospheric gases, some very simple chemicals in the atmosphere, and you combined them with some kind of energy, like a lightning or a spark discharge of some kind, ultraviolet radiation, that those simple chemicals would combine and recombine and form more complex chemicals. Things like, for example, amino acids. And I'm going to use this little snap block as an illustration of an amino acid building block. And those amino acids would eventually form proteins, linking up and forming long chains like this. And other simple chemicals like sugars and things called bases would link together and form the DNA molecules. And you get these larger molecules would then be enclosed by a cell membrane or some kind of primitive thing like a cell membrane. And those primitive little cell-like things would compete with each other for survival, eventually get more complex, and after millions or hundreds of millions and even billions of years, voila, you would have life. Okay? And that was the scenario, the story that was entailed by this idea of chemical evolutionary theory. Not amoeba to man, but chemicals to a cell. Okay? Now, in the late 19th century and the early 20th century, this idea seemed very plausible because scientists thought the cell was effectively something very, very simple. One of my favorite quotes from a 19th century scientist is from Ernst Haeckel, a German Darwinist who said the cell is a simple homogeneous globule of undifferentiated protoplasm. Translated, it's like Jell-O, okay? And if you think of the cell, if you think of the simplest unit of life as something very, very simple, then you can imagine how it could have come out of the soup very easily, that a few simple chemical reactions could have occurred, and poof, you've got life. The difficulty for the chemical evolutionary perspective has come as layers and layers of increasing complexity have been revealed in that tiniest unit of life. By the way, for just to make sure we're all on the same page here, a cell is the tiniest unit of a living organism. There's some animals that have just one. Our body has literally trillions of cells. Okay, so we're made up of these smaller units, and they turn out to be extraordinarily complex. So there's a kind of a simple rule or metric in this field. The simpler life appeared to be, the easier it was to explain by reference to simple chemical evolutionary processes. The more complex life has been revealed to be, the more difficult it has been to explain by those same kinds of mechanisms. So what I'm going to do now is kind of give you a little excursion into the inner workings of the cell and talk about some of its key parts. And in the process, I think we'll see why, first of all, why the scientists have become convinced that the cell is very complex, and secondly, why that has posed a great problem to this idea that you could evolve life in an undirected process from chemicals alone without any intelligent direction or guidance. That's the corollary to the idea of apparent design in biological evolution. You've got the chemistry just reacting with itself and producing life. It looks complex at the end, so it looks as though it was designed, but it really wasn't because you had this chemical evolutionary process at work. That theory is now under very severe scrutiny. In fact, I think it's in really serious shape. Okay, if we can look forward. Some of you may have seen in the textbook, Chuck mentioned the disparity between what scientists know and what we continue to teach our children in high school biology textbooks, for example. Most of us have heard of if you've taken a high school biology class, you would have seen a diagram like this. This is the famous experiment by Stanley Miller that was conducted in 1953. Miller was able to synthesize a few amino acids by sparking some of those simple chemicals. They were atmospheric gases, ammonia, methane, hydrogen, and he got an amino acid or two, 3 or 4 actually, to form in the bottom of his experimental vessel. And this was heralded at the time as a great breakthrough for the theory of chemical evolution. We'd gotten to that step of forming the basic building blocks. Now, if we could back the slides up just one, to where we were, we'll see that actually all Miller accomplished was getting from step 1 and 2 to step 3. He never got beyond that. And moreover, since that time, we've learned that the evidence from geology and geochemistry suggests that the gases that he had in his experimental apparatus did not actually match what the early Earth's atmosphere was likely to have been. If there was even a slight amount of oxygen on the early Earth's atmosphere, it would have quenched all these important reactions that move in a life-forming direction. And it turns out now there's evidence that there was considerable amounts of oxygen in the early Earth's atmosphere. And so this experiment does not simulate anything, really. It was just, now we just think of it as an interesting experiment. But nevertheless, it continues on in the textbooks as sort of textbook orthodoxy about supporting the idea that life could have come from simple chemistry. So, word to the wise, if you're concerned about what your kids are learning in the high school, you don't need to make an appeal specifically to the Bible and say, gosh, this theory of evolution goes against the Bible, using the Mars Hill example that Chuck mentioned of appealing to people on their own terms. You can talk to your science teachers and say, look, the stuff in these textbooks is just out of date scientifically. Nobody takes these experiments seriously among practicing origin of life biologists. Miller himself has said that they're no longer relevant to explaining the origin of life, his own experiment. Okay, we can go ahead to now. Okay. Now, there's an additional difficulty with the Miller experiment. Let's say you were able to synthesize one of these building blocks. Does that give you life? Or even, does it give you a protein? The amino acids are said to be building blocks of proteins, and proteins are long chain-like molecules. And here I'm going to introduce these toys. It says on the box for ages 2 to 4, so I thought it would be appropriate for all of us tonight. People ask me, do you give those back to your kids when you're done? And, the answer is actually no, So I'm going to illustrate the concept of a protein. We think of proteins as things we eat, and that's true. But proteins are really the important molecules in the cell. They're the cell's toolbox. They do all the different kinds of jobs. And there are some proteins that are enzymes. There are some proteins that send signals. There are some proteins that are building proteins that build structures. Muscles are made of proteins, the cell's skeleton is made of proteins, and each one is very different, and they have very specific and complex three-dimensional shapes. So they line up, when you get the amino acids hooked together, the proteins will, because of their mutual chemical interactions, fold up into complex structures. Now, the picture you see on the screen up here is a very complex three-dimensional, it's a tangled web of amino acids. And it's the protein, it's whale myoglobin, which is similar to the hemoglobin that we have in our blood that carries oxygen. And the great surprise that came upon the biological community when this was discovered can't be underestimated. In 1958, people were thinking that the ultimate secret to life would be something very simple, like a pile of neatly piled logs. Proteins would be like neatly piled logs or hats stacked on each other, or something regular and simple that could be explained by law. And instead they found the ultimate secret of life, proteins, were very messy. And this intensely complex, jangled structure here is the amino acids that fold up to make this oxygen carrier, myoglobin. Okay? So one of the first discoveries of biology that began to cast doubt on this simple molecules from chemistry to life idea was the complexity of these proteins. That the toolboxes in the cell, these tools, had these incredibly complex structures. And moreover, these structures had to be exactly the way they were in order to perform the functions they do. So if you think back on Stanley Miller's experiment, just getting an amino acid or 2 or 3 or 10 by itself is really not very significant. What needs to happen to form something that can actually live is you've got to link the amino acids up into long chain-like molecules that then form very specific three-dimensional structures. Okay, and they have a kind of a lock and key fit, or a hand and glove fit with other molecules in the cell, and that's what enables them to perform their function. So I'm going to show you a couple more pictures of some things that proteins do. They have they have very specific three-dimensional shapes, and that enables them to bind with other molecules which have matching shapes. So there's this, not only the idea of complexity, of irregularity, but also of specificity. It's very much like a key. A key has a very irregular shape, but in virtue of that, it can fit precisely into a lock and perform a function. If it's even a little bit different, you try putting that same key in, and the lock won't turn. You may not even get it in the hole. And so it's that hand in glove or lock key fit that it was really impressive as people began to discover not only how complex proteins were, but how specific they were. Okay, and that was not something that was explained simply by getting some amino acids. All right. The next slide then is going to show another of this same kind of idea, this lock key fit. Here's the big blob of all those things is an enzyme, and there's a little pouch there, and for the enzyme to catalyze an important chemical reaction in the cell, it's got to have exactly the right shape pouch for this other little substrate to fit in, and then, good things happen chemically if you've got that lock key fit. This is really very profoundly against the idea of chance. Things are very precise and specific, okay? Now, it turns out you'll be tested on this, okay, this formula. Chuck will pass them out. No, I'm kidding. Okay. The one-dimensional sequence of amino acids determines that three-dimensional structure that's so important to function, okay? What this shows is that it's not just arranging, I've got my amino acid building blocks up here. It's not just a matter of arranging these in any old order. It's not even just a matter of getting them to link up. It's sequencing them in a very specific way. If you get the amino acids in the right arrangement, then the protein will fold into a functional three-dimensional shape that will have a lock key fit with something and perform a function. And Francis Crick likened this early on to the idea of an alphabet. And indeed, you might think of the typesetting blocks that people used to use to make the newspaper headlines. Every one of the blocks, the little square blocks, you dip in the ink and you press it, the old typesetters would use. Every one of the square blocks is identical, and that's what you find with the amino acids. The backbone is the same in every one, but they have little sticky-outy parts. The chemists call them side chains. Okay, and the little sticky-outies are analogous to the letter face on the type block. The block is the same with every letter, but there's a little sticky-outy part that's different. Just as in the newspaper case, if you sequence the letters in the right arrangement, you'll get a functional headline, something that conveys information. You've got the same kind of thing in the case of the amino acids. It's not just having the blocks, it's getting them sequenced right, so their little sticky-outy side chains are in the right sequential order so that the protein folds up and forms a functional entity, something that will actually do a job, okay? Now, we call this property sequence specificity. And that's a kind of a big word, but it simply means that the sequential arrangement of the parts determines the function of the whole. You can't get a functional sequence of letters unless you're spelling according to English conventions. You can't convey information unless you sequence your letters in the right way. You can't get a functional protein unless you get the amino acids sequenced in the right way. They're sequence specific. It's not just a matter of having amino acids or even linking them up. It's sequencing them, just as we would do with letters. If I want to spell something interesting, I don't just reach in and throw them on the floor. I've got to sequence them in the right way. And so this is an amazing property that was discovered about biological objects, about the key molecules in the cell. They had this extreme specificity of sequencing, just like a language. And this was something that was very early. The early discoverers of this saw this connection right away to language. Francis Crick was one of the first ones. Now the question is, where does this come from? How do you explain that? How do you explain sequence-specific sequencing of amino acids? Can you explain that by chance? It seemed very implausible to people. Well, the next slide will show that in an actual living cell, this turns out not to be mysterious, because on the DNA molecule, most of us have heard of the genetic molecule DNA, the famous molecule of heredity. There is a 4-letter alphabetic code that actually conveys instructions to the cell about how to sequence the amino acids. So the explanation of how the amino acids get sequenced properly resides in the DNA molecule. The DNA has a code. It has a 4-letter alphabetic code that explains where that sequence specificity comes from. Well, we all sigh, end of mystery, right? Well, the problem is that when we talk about the instructions on the DNA, we're just talking about sequence specificity all over again. The chemists represent the 4 letters are arranged in a way like, that we can convey information with just 2 letters, right? In a binary code in a computer, 0 and 1, okay? We can convey information with 26 letters. And it doesn't really matter what you make the stuff out of. You can use, I've got these little Scrabble pieces that are made of plastic. We can use that to convey information. We can use smoke with a skywriter. And the same thing applies in the cell. You can use chemicals. And depending on how you arrange them, they can send and convey messages. And so the DNA has a four-letter alphabet. Chemists represent that with the letters A, T, G, and C. And depending on how those four chemicals are arranged, you'll get a different protein built in the cell, or maybe no protein at all. So if you ask, where does the information-like character of the protein, the sequence specificity of the protein come from? The answer is, it comes from the informational properties of DNA, from the code that's written in the DNA molecule. Okay, so mystery solved, right? Wrong. What's the question that raises? Yeah, where's the information on the DNA come from, right? It just pushes it back one generation. And so in the whole field of what's called origin of life studies or origin of life biology, the big $64,000 question is no longer how do you make amino acids out of simpler stuff? Were the atmospheric conditions conducive to making amino acids or sugars or bases? The big question is now, where does the information come from? How do you get the information into the DNA? Okay. Bill Gates has said that DNA is like a software program, only much more complex than any we've been able to write. And the challenge of the chemical evolutionary theorist is to explain the origin of that biological software without reference to a programmer. Okay? And because that's the natural thing that quote suggests, isn't it? That if you have information, if you have a software code, you must have a programmer. We've got a little bit of animation now that will kind of make some of these points really clear. And what you're going to see first, the first frame here shows a folded protein, and the animator is going to unwind it for us so that we can see how proteins are formed from these building blocks, these amino acids sequenced in a very particular way. Okay, and then we're even going to do a flyby. So what we're doing right now is we're taking you inside the cell to see what one of these proteins. Now, by the way, you have hundreds of proteins in every cell. Each one does a very different job, and so you are really fearfully and wonderfully made. Okay, now in the next frame, when we get done unwinding this guy, we're going to see our own oxygen carrier, which is hemoglobin. And this is just a marvel of engineering. I met a med school professor who was a molecular biologist at Emory last fall, and he gave me his testimony and told me how he got saved by studying the hemoglobin molecule. And somebody quipped, "There's power in the blood," you know. Anyway, this is you see these little caverns. This is a 586 amino acid long protein that folds up into this very exquisite structure that enables it to capture molecular oxygen in your blood. Mutations in even one amino acid site can cause deleterious consequences in disease. It's exquisitely designed, just this one molecule. Now, this next frame shows us the DNA as it is the famous double helix, and the animator is going to unwind this now and show the information-bearing properties. The chemicals, on the outside you have phosphates and sugars linked together. That forms the backbone. But on the inside, there are molecules called bases, and there are 4 of them. We represent them with the letters A, T, G, and C. And again, depending upon the sequence of those letters, the A, the T, the G, and the C, we can build functional proteins or not. So DNA also has this property of sequence specificity, where the sequential arrangement of the parts determine the function of the whole. In this case, a communication function, actually sending informational signals that allow the cell to build the right protein constituents. And so here, I love this way the animator has done this, winding it for you to see the way the message goes up the longitudinal axis, the length of the molecule. And there's enormous information carrying capacity in every DNA molecule in your body. In fact, I don't know if this is still true, but a few years ago, it was said that the information carrying capacity of the DNA molecule in a eukaryotic cell, we can pause this now, it was 45 trillion times that of our most advanced superchips. And I'm sure our super chips have advanced a bit, but they've got a ways to go before they catch up with the design that's already built into your cells. Okay, so that's a little primer on biology. It gives us, I think, some appreciation of just how immensely complex even the simplest things are. The cells that we take for granted, the molecules working inside the cells. If you cut yourself tonight and bleed a little bit, with the right kind of microscope, you can isolate the DNA and look at it. And to us under the microscope initially, it was called chromatin. It looked like just kind of nothing stuff. But as we learn more and more, it's densely packed with information. This slide is for Chuck Missler's benefit, and probably only, but as an information scientist, he'll appreciate this point, which is that to build proteins, you need information on DNA. But it turns out that the proteins are needed to process the information on the DNA strand. There are certain proteins that are needed to unwind the DNA, certain other proteins that are needed to read the DNA sequence. And all of those proteins have to be themselves built. And they're built by the instructions on the DNA. So you need DNA to build proteins, but you also need proteins to build DNA. And you don't need just one protein. You need, what they call the minimally complex cell, you need over 100 proteins. And so there's a complex information processing system in the cell. It's not just one strand of DNA sitting there in isolation. It's a whole functionally integrated system. And the complexity of this is mind-boggling. And my father, like Chuck, is an engineer by training. And when I showed him this, he said, "Oh, those are closed loops." This is engineers recognize this as a sophisticated design strategy. And this is another of the problems that origin of life biologists have to contend with. Not just the origin of the information, but the information processing system, the whole functionally integrated way of expressing information where each part depends on another part, which in turn is the cause of that part. So you've got this circularity. Okay. Now, the question is, how do we explain all this stuff? In particular, we're going to focus on just the question of how do you get information at all? And if we go back to those the pacemaker example I used, we talked about design, we talked about chance, we talked about necessity. And what we're going to do is we're going to think about what it would take to explain the origin of information by reference to these different categories. Or in other words, what's the best kind of explanation to invoke to explain the origin of information? Okay? And this little schematic I have up on the screen is derived from a new book called The Design Inference by Bill Dembski. What Dembski does is he's a very sophisticated information scientist who says, look, we tend to explain things in one of three ways. We either invoke chance, or we invoke physical law or necessity, or we say things were designed. And the question when we encounter information is, what's the best kind of explanation? Okay, what's the best kind of explanation to use? So we're going to look at each of these. Let's look at the chance explanation first. I think actually we've got a funny quote it's not really funny, but it's ironic. Next quote on the slide. This is from Francis Crick. He says that biologists must constantly keep in mind that what they see was not designed, but rather evolved. Okay? So you just from the few things that I've shown you, you can see why that appearance of design, that impression of design is well nigh overwhelming for many people who live in biology, or who work in biology. We all live in biology. And Crick is giving a kind of confession here that he says, we have to constantly pinch ourselves and remember, look, we're evolutionists, we're Darwinists. Okay, the question is, can we explain the information without invoking design? What are the options? Well, the first one is chance. So let's look at that. Let's imagine that we want to spell a short informational sequence, like how did life begin? Okay, and what do we have to do that? Now, what we're going to do here is construct an analogy. And we're going to say that building a protein is like constructing a short, meaningful sequence, like how did life begin? Okay? Now, in the biological case, the first thing you have to do is you've got to get your building blocks, your amino acids, to link together. Okay? So you want to get the amino acids to link together. And it turns out that in chemistry, there are two kinds of bonds between amino acids. There are things called peptide bonds, and again, you're going to be tested on this later. No. Okay, some of these terms you can just kind of let pass and get the main concept, okay? But there are peptide bonds and that link them together, and there are non-peptide bonds that put them at funny angles, okay? And this is the chemistry of a peptide bond here for those who are very interested. Now, the point is, to get a functional protein, you have to have a peptide bond at every site, at every linkage point. Okay? Now, a short functional protein might be something on the order of 100 amino acids long. Many proteins are thousands of amino acids in length. An average length one would be 300 amino acids long. But let's just do it for a short a protein of 100 amino acids long. That means the odds of getting just the correct linkages at every site are, got 1 in 2 chance of getting the right bond here, 1 in 2 chance of getting the right bond here, 1 in 2 chance, anyone, the facility with mathematics there, 1 in 2 times 1 in 2 times 1 in 2. With 100 amino acids, you've got 99 linkage points, so that's 1 over 2 to the 99th power. That's a big number, okay? That's 1 chance in 10 to the 30th is the way that computes, all right? Now in other words, it's very improbable that you'll just even get the right kind of chemical linkages to form a protein, okay? Now, in our analogy to language, our next slide shows that would kind of be like, for those who can't see, be like having half of your alphabetic letters tipped on their sides, all right? Now, the biological case is actually more restrictive because if you get even one non-peptide bond, the protein won't fold properly and it won't perform a function. We can still make the sense of this message out even with the W tipped on its side and some of the other letters. We can still see that it probably says, how did life begin? So biology is even more restrictive than language on this case, but nevertheless, you get the idea from the analogy. Okay, there's another probabilistic hurdle, another condition that has to be met. And that is, and the next slide illustrates this, is that these amino acids that I'm representing with these little blocks come in both left-handed and right-handed versions. Okay, they're called isomers for chemists. And it turns out that to build a protein, you can only have the left-handed version of the amino acids. Okay? If you have even one right-handed version in your chain, again, it doesn't fold properly and you get no function. So for a protein 100 amino acids in length, you again have the same kind of probabilistic difficulty. You've got a 1 in 2 chance of getting a left-handy, not a right-hander. You've got another 1 in 2 chance. It's 1 in 2 times 1 in 2 times 1 in 2 times 1 in 2, 100 amino acids. 1 in 2 times 100 power. Again, you've got a very big number. It computes to, again, roughly 1 chance in 10 to the 30th. And those probabilities are independent, and so you multiply them together, and to get the right sequence, or the right bonds, and the right kind of isomers, the left-handed ones, not right-handed ones, you have only 1 chance in 10 to the 60th of getting those 2 conditions met. And that is the chance of building a functional protein by chance, okay? Now, just to get a handle on that, I think there are something like only 10 to the 65 atoms in our whole galaxy. So this is like finding a single atom in all of the particles that exist in the galaxy, something on that order, a couple order of magnitudes off. But, the probability, this is not very good. Now it gets worse because there's yet a third condition, and this is the most important at all. Remember, we said that these molecules were sequence specific. You got to get the right kind of connections, and you've got to get the right-handedness, but you've also got to get the right amino acid. It turns out there are 20 proteinaceous amino acids. I don't know how many I've got represented here with the different colors. And they're like, just as we have in English, a 26-letter alphabet. There are 20 letters in the amino acid, in the protein language, in the protein. And so your chances at any given site are roughly 1 in 20 times 1 in 20 times 1 in 20 times 1 in 20. Now, it's not quite that restrictive because at some sites there's variability allowed, at other sites there isn't. But it comes out on average to about a 1 in 5 chance of getting the right amino acid at a functional amino acid at each site. And when you factor that in, the odds of getting a single short protein, 100 amino acids long, come to be about 1 chance in 10 to the 25th power. If you have an even longer protein on the order of, say, 150 amino acids, you get numbers like 1 chance in 10 to the 180th, and you're well above an important theoretical boundary that has been fixed by probability theorists called the universal probability bound. And that's the number past which appeals to chance become unreasonable on the cosmic scale. And that number is, by the way, if you're interested, 1 chance in 10 to the 150th. So even a short protein, the odds of building even a short protein exceed what you can expect to happen given what our math geeks call the probabilistic resources of the entire universe. Okay? Now let me explain that idea. Imagine you are I think I can illustrate it. Imagine you've been sentenced to you've come before a judge, and I'm the judge, you've done wrong, and I give you your choice. You can either spend 10 years in prison, or you can flip a coin 1,000 times until you get 1,000 heads in a row with no intervening tails. Okay? You go along 342 times and you get a tail, sorry, back to jail. Do not pass go, do not collect $200. Okay? The question is, what should you, as a probabilistically astute criminal, do? Take the 10 years, okay? This is the concept of probabilistic resources. It's not just a matter of how improbable something is in the abstract, but how improbable something is given the amount of time, the number of trials that you could have flipping your coin in this case. Now, origin of life biologists have reasoned in a very similar way, and they've said, okay, granting a 20 billion year old universe and a 4.5 billion year old Earth, and maximum possible reaction rates between all the chemicals that would have been involved in the soup, what are the odds, given all that we could develop even a single protein by chance in the time available on the early Earth, or, since the Big Bang or whatever? And they've said, you know what? They're very much like the odds of the criminal getting 1,000 heads in a row in the 10 years that he has available. We don't have enough time. We don't have enough trials. And so the chance hypothesis, since about the mid-1960s, has been effectively dead in origin of life studies. Now, this is not among Christians or people who call themselves creationists. This is among those leading theorists of the chemical evolutionary idea. And what's brought them to that conclusion is the immense complexity of the proteins, of the DNA, and of the whole cellular complex. It's just too vastly complex to have come about by chance, given the known time of the universe, conceding a very old and ancient universe, which some of you may not concede. Okay. Now, I've given this talk at secular science departments and universities, and at this point, usually I get, this kind of, people can no longer stand listening to this, and the hands go up, and especially among the sophomore students, and they want to contest this point. And I always tell them, look, this is not the point to die on your sword. This is, when it gets controversial, I'll tell you, okay? Or my dad used to have a poster in his office, when I want your opinion, I'll give it to you, and this is the chance hypothesis is not controversial even among those secular naturalistic chemical evolutionary theorists who are trying to think of a naturalistic explanation for the origin of life. They're thinking of other options than that. It doesn't seem plausible to them. Okay, so if you go out and have one of those, Whitworth, we have a drinking policy, so I always say, have a Coke with your friends and talk philosophy. Don't allow yourself to be drawn into an argument about chance, because that's not where the action is. Okay. Now, for a time, the idea was there was another idea. In fact, what do we have? Oh, we've got some more. We're continuing with our analogy. We see if we've got everything all mixed up. So that some of the letters are tipped upside down, and some are backwards, and some are out of order. That's what you're going to get by chance alone. One scientist here says that blind chance is very limited. Low levels of cooperation or organization he can produce exceedingly easily, the equivalent of a few letters and small words, but he becomes very quickly incompetent as the amount of organization increases. I always illustrate this with my freshman students. I won't do it to you because you're actual grown-ups. The lack of efficacy of chance, that as an information builder, I have a bag of Scrabble letters, and I just say, okay, let's test the explanatory power of chance as an information builder. And I just pass the hat through the class and ask people to go up and write down the letter that they pulled out. Now, occasionally, usually you get gibberish, of course, but occasionally I'll get a short sequence like ran or cat or something like that, and the students always wanting to prove their professors wrong will start to hoot and holler and do cat calls, but I always win. Okay, do you know how I always win? Chuck called this the N+1 problem today. I just run the experiment a little longer, because sooner or later, more gibberish comes out, and the gibberish swamps that's a new word, swamp. It swamps the meaning. Okay, so chance is not going to do it for you. Okay, another idea though, and this is the idea known as prebiotic natural selection. If you remember your Darwinism, from high school, remember the Darwinian mechanism was not just brute chance. The Darwinists wanted to combine chance or random variation with the mechanism of natural selection. So you have a little change, and then the survival of the fittest principle kicks in, and the changes which are advantageous are produced or are preserved, and the most fit offspring survives. Problem with that is the key word offspring. Okay. Natural selection only works if you already have life. Okay, it's differential survival among the next generation, or sometimes it's called self-replication. Okay, natural selection presupposes organisms or animals that divide and copy themselves, have offspring, and then natural selection picks the most fit among the offspring. But we don't have the luxury of life yet. We're trying to explain the origin of life in the first place. So invoking prebiotic natural selection to explain the origin of DNA and protein is a contradiction in terms. In other words, natural selection presupposes self-replication. But self-replication presupposes the existence of DNA and protein. It's DNA that divides and copies itself in the process of reproduction. But the thing we're trying to explain is the origin of DNA and protein. So to invoke natural selection to explain the origin of DNA and protein is begging the question, because you don't have natural selection unless you have self-replication. You don't have self-replication unless you have DNA and protein. So you're invoking the very thing you need in order to explain the thing that you're trying to... here's a better way to think of it. There was a man who went and fell in a hole. Okay, he needed a shovel to get out, and so he went home and he got the shovel, jumped back in the hole, and dug himself out. Okay, this is what the advocates of prebiotic natural selection are doing. They need information in the form of DNA to have natural selection, but that's the very thing they're trying to explain in the first place. Okay? And so, no less an authority than Theodosius Dobzhansky, the dean of evolutionary biology in the 1960s and 70s, said that prebiological natural selection is a contradiction in terms. And yet I still hear people talking about this, but it's not a serious theoretical proposal anymore. Okay, next slide, I think amplifies that with another, a larger quote for real science geeks here. Both nucleic acids and proteins are required to function before selection can act at present, and yet the origin of this association is too improbable to have occurred by natural selection. Okay, so it's the same kind of catch-22. All right. Now, in the face of the difficulty with chance and with the Darwinian idea of chance and natural selection acting together, scientists starting in about the late 1960s and early 70s came up with another idea. And this came under the heading of necessity or self-organization. There was a book that was published called Biochemical Predestination. And this was not published by a leading Calvinist theologian, okay? This was a chemist, and his idea was very simple, really, and it's easy to understand. The idea is that just as ions of sodium and chloride, you know, the basic chemistry, the sodium, the Na has a +1 charge, the chlorine has a -1 charge, and you put them together in a solution, and boy meets girl, there's chemical attraction, you know, the plus charge and the minus charge come together, and you form a crystal. Okay, and crystals are highly ordered, highly organized. NaCl, NaCl, NaCl. They have a wonderful structure. We call it a lattice. Okay, and the scientists who thought of this idea of biochemical predestination or self-organization was thinking that maybe life formed in a way analogous to crystallization, similar to the way crystals form, where chemicals are attracting each other. Okay, and so because after all, what needs to be explained is the order or the sequencing of a protein. Well, if crystals can be explained by forces of chemical attraction, bringing their different parts together, maybe proteins and DNA molecules could be explained in the same way. Do you see the basic idea that this is not chance variation, things just kind of randomly, haphazardly happening. This is rather things sticking together because of chemical forces that function by necessity, that have to happen. Okay, well, a necessity thing we often relation is like something like a law of nature. If something's very probable, so probable that in fact we know it's going to happen. Anyone doubt that this is going to drop? Okay, all right. We say that happens by necessity, by the laws of physics. In this case, the law of gravity. So necessity are things that have to happen because of the laws of physics. And the idea was that maybe the sequencing in proteins, the sequencing in DNA, which we refer to as the information, maybe that came about because of these forces of attraction between the constituent parts, the individual parts in the DNA and the protein molecules. And that was the idea of self-organization, biochemical predestination. Things are predestined to organize themselves because of their forces of chemistry. Now, that happens to be where the action is. If you get into a debate with a naturalist who doesn't want to accept the evidence of design in biology, they'll be holding out for a self-organizational explanation. Okay? But there's some fundamental problems with that are actually extremely exciting. Sometimes it's the case that when people make a bold proposal that's wrong, you learn a lot from it. And I think this is a bold proposal that's wrong that we learn a lot from, and it really will give us some appreciation of how profound the information-bearing properties of these DNA and proteins are. Let's just, in the protein case, for people who are taking notes who are really into this, it just turned out that as a matter of fact, there were some slight affinities between some amino acids and others, but that they didn't correlate with known amino acid sequencing. Okay, so there were some amino acids did slightly prefer to be near others rather than some others, but it didn't really explain the actual proteins that we have in life, because it didn't correlate to the sequencing that we see. That meant something to you. Take notes on it, okay? But I've got a simpler way to explain this, and it relates to the DNA molecule, okay? I realize it's kind of like this is like when I watch cartoons with my kids. There are people that are science specialists out there, and there are people that are lay people. So I want to make sure that people can understand this on two levels. Actually, what happens is my kids understand the cartoons and I don't. But that's okay. This is the DNA molecule, and the DNA molecule has some very peculiar properties. If you look at the side, I'm going to take the handheld mic and just walk over and point. I should have brought one of those little laser deals, but the backbone of the DNA has these little pentagon-shaped things. Those are sugar molecules. And then these little circles, and those are phosphates. And there are chemical bonds between them, and they link up and they form this nice solid backbone, okay? But that's not where the message is, okay? The message occurs in the long axis here, with the C's, T's, G's, and A's. Okay? And depending on how they're sequenced, you can either build functional proteins or not. That's where the information is stored in DNA. Now, what's interesting about this is that in this axis, there are no chemical connections between the individual parts in the message. Okay? So remember, the theory is, the self-organizational idea is that we're going to explain the sequencing of the information-bearing part of the molecule by reference to forces of chemical attraction. But it turns out that there aren't forces of chemical attraction at work in the direction of the message. Okay? Now, I've got a way to illustrate that, because I know I've just lost 60% of the audience. They say with every equation you put in a book, you lose 10,000 readers. I don't know what happens when you put up chemical diagrams. But here's a message, okay? This is Koinonia house, okay? We'll just take off make it K house here for simplicity. Now, there are forces of attraction between the letters in this message and the backbone here, okay? The blackboard, this magnetic blackboard here corresponds to the sugars and the phosphates, the pentagons and the circles with the P's in them. That's, in the DNA, those circles and pentagons are the backbone of the message. But that's not where the message is. The message is in the stuff that's stuck to it. Okay? Same thing here. We've got the backbone, or the backboard, and then we've got the message stuck to it. Okay? Now there are forces of attraction that hold the individual constituent parts in the message to the backbone. Okay? But those magnetic forces here do or do not explain the origin of the information contained on this blackboard. Do not. Do you see the point here? My kids write little messages on our refrigerator all the time. The magnetic forces explain why the letters stick, but they don't explain the sequencing. And again, you have the same thing. There is no physical chemical interaction here between the letters. So what the information theorists, and in particular, one deeply insightful physical chemist named Michael Polanyi, we've got a quote from him next, is that the information in DNA is extrinsic to its physical chemical properties. It comes from outside the physics and chemistry. Now, this makes a lot of sense if you stop and think about it. None of us would explain the origin of the information in the headline on this morning's newspaper by reference to the physics and chemistry of ink and paper. Okay? So, something more than ink and paper is responsible for that message sticking, or the sequencing of the English letters that say that Yankees win the World Series. Okay? The information is coming from outside the chemistry. On the refrigerator at my house, the information comes from little mines, okay? And so in the next slide, there's a quote from Michael Polanyi, a famous chemist who said, as the arrangement of a printed page is extraneous to the chemistry on the printed page, so is the base sequence in DNA extraneous to the chemical forces at work in the DNA molecule. All right. Now, this is really a profound thing, and I hope this makes it clear, okay? The idea is that the information is coming from outside physics and chemistry, all right? Just from a matter of the evidence, the forces of attraction that the self-organizational theorists talk about simply don't exist. Just as there are no forces between the letters that dictate the sequencing, there are no forces between the parts of the DNA message that determine its sequencing, okay? But there's an even deeper thing that can be said about this. I want you to think for a minute about what would be the case if there were forces of attraction that could explain the sequencing. What would you have then? Would you have an informational message? Imagine if every time you got an A, you got a T. Every time you got a T, then you had to get an A because of these forces of necessity. And every time you got a T, you had to get another A. And every A brought another T, and another T brought another A, and another T brought... What would you get? Would you get a message? Or you get a repeating pattern like A, T, A, T, A, T, A, T, A, T, A, T, I like to say you get a mantra, not a message, okay? You get a repetitive sequence. And that's another way of saying that self-organizational properties, forces of chemical necessity, physical chemical laws don't produce interesting, unpredictable informational sequences. To be or not to be, that is the question. You look at all those letters, they don't repeat over and over again. Physical chemical laws, forces of chemical necessity, produce repetition, like that crystal in our original example. NaCl, 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 NaCl. The forces of physical chemical attraction produce repetition, redundancy, simple order, but not information. So what we can say is that if it were the case that some of those physical chemical laws of attraction were discovered, then we wouldn't have information anymore. They're categorical opposites. If you've got physical chemical necessity or physical chemical laws, you don't have information. Information is aperiodic, unpredictable. It's a sequence of letters that doesn't follow a repeating pattern. Okay? So this is really important because it's not just that we haven't discovered physical chemical properties that can explain the origin of information in the cell. We could never discover such properties because if we had them, we would no longer have information. Okay? So I think the self-organizational program, which is the place where all the action is, where the naturalists are holding out their hope, is fundamentally flawed. It's incoherent theoretically. We will never solve this problem. It's like squaring a circle. Making laws produce information is like squaring a circle. Okay? So, if it's not chance, and it's not necessity, and it's not the combination of the two, what is it? What can produce information? Well, we know something about that. It's not that we know there is an entity in the universe that is capable of producing information. And that entity is called intelligence. Okay? Now, I want to illustrate just this conceptually for those who can see the slides. I just talked about the idea of a repeating order. AT, 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 NaCl, NaCl, NaCl. Information theorists call this quality or property redundancy or simple order. Okay? That's not what's in the cell. What's in the cell is more like a software program or a section of English text. Okay? So that's not what needs to be explained. It's not order. Next slide will show another property of sequences of characters, and this is called complexity or sometimes randomness. And this is the classic monkey at the typewriter example, or the noise on your TV screen on channel 59. Okay? This is just random stuff. Okay? Now, the random things are very complex, very unpredictable. They're not repeating over and over again, but they aren't significant either. There's no information because they're not specified. Okay? In the cell, we have, which is the third illustration, we have meaningful text or we have sequences which are both complex and functionally specified. They perform a job, a communication function. And we find this property, which we sometimes call specified complexity. I called it sequence specificity before. Some people just call it information. This is what we find in language, this is what we find in computer programs, and this is what's in DNA, and this is what needs to be explained. And then the question is, how do we explain it? And I think the answer, as we've looked at these different broad approaches, is the only known cause of the origin of information, of specified complexity, is information. And the next slide gets that across in a couple of ways. Here's the quote I mentioned from before from Bill Gates, that human DNA is like a software program, only much more complex than any we've been able to devise. I like this cartoon in the slide. You see the DNA represented with the sequence of C's, T's, A's, and G's next to the binary code with a series of zeros and ones. It's precisely analogous. They're both information bearing. And so if you think hard about what Bill Gates is saying and what his quote implies, this suggests that the most rational explanation for the origin of the information in DNA is actually a programmer, a mind, an intelligence. Now, this connection between intelligence and information is something that we recognize all the time. One of my favorite design inferences happened for me going into Victoria Harbor up in the northwest. If you go from Seattle on the ferry, you can go all the way up into Victoria. And there's a mural of flowers on the hillside. And as I got closer and closer, suddenly I drew what we call a design inference. I inferred that gardeners had been at work. It was not wind and erosion. It was not natural selection. It was the result of an intelligence. Now, why? Well, it turns out that the pattern of red and yellow flowers spelled out a message. Welcome to Victoria. Now, everyone on the boat made the same inference, so they probably weren't nearly as interested in it as I was. But the point is that information is a hallmark of mind. It's an indicator. It's a diagnostic. When we see information, we infer that a mind was behind it, that an intelligence was behind it. So when we see information in the cell, the most natural thing to infer is that it has an intelligent source, that an intelligence put the information into the DNA, or created the DNA with the intelligence in it, or the information in it, okay? Here's another. This is a hieroglyphic inscription, okay? You think of the Rosetta Stone, or an inscription. Now, I don't actually read cuneiform, but there are archaeologists, I'm told, who do, and they figured out that this was not just a random set of markings produced by a natural cause. They made an inference to an unnatural cause, to an intelligence, namely human intelligence. This contains information, therefore it must have been designed by an intelligence. Same connection. Okay, next slide. Now, the way we're reasoning in this area turns out to be the standard way that scientists reason in every historical science. What we're doing is we're comparing competing possible explanations for the same effect. The effect that needs to be explained is information. You might think of a footprint in the snow. And there you have a piece of evidence, and you're wanting to reconstruct what happened in the past to explain the origin of that footprint. Now, we happen to know that only feet make footprints, so when we find that footprint, we can infer that there was a foot there in the past. But it's not always that simple. There are some things that might have multiple possible causes. So what we've done in this little talk tonight is we've looked at several possible causes for the origin of information. And next slide will show that the historical method attempts to eliminate those causes which are not sufficient to produce the effect and leave only that one cause which is known to produce the effect in question. And so what we've done tonight, in the next slide we'll show this, is look at information or specified complexity and ask what are the types of causes that might produce it. And we've looked at chance, necessity, and the two in combination, and for different reasons, but very fundamental reasons in each case, we've shown that each is insufficient to produce information. That leaves only one cause that we know to be sufficient to produce information, and that's intelligence. So when we encounter the information in the cell, without the benefit of getting to see exactly what happened, we can infer that there was an intelligent cause behind that information. Just as if we can encounter a footprint in the snow and don't actually see the person who made it, we can still, with reliability, infer back in time to a foot as the cause, okay? So we're moving from the effect back to the cause, okay? Now this is a well-known method of reasoning that's employed in the historical sciences. It's sometimes called the method of multiple competing hypotheses. It's sometimes called inferring to the best explanation. And what's interesting is that none other than Charles Darwin himself used this method. Here, one more slide shows the way we've applied this to the question of information. Chance wasn't sufficient, necessity wasn't sufficient, and chance and necessity together aren't sufficient. Only design is sufficient to produce information. Now, Darwin himself used this method, and he was accused of having a theory that was not based on repetition in the laboratory. He couldn't replicate his experiments. And he said, well, but look, guys, I'm an historical scientist. I'm trying to explain the evidence that we have before us after the fact. So I'm looking for the best explanation. And he uses this phrase, he says, it seems to me that supposing such hypothesis, he's talking about his theory of common ancestry, were to explain the general propositions, the facts that he mentions above, we ought, in accord with a common way of following all sciences, to admit it until some better hypothesis be found. So this is the method that he used, okay? And so we're using the same method, the same standard method, to argue for design that are used in the historical sciences, including in evolutionary biology. So we're not appealing to the Bible or to religious authority. We're appealing to evidence and using the same method. Now, how have our naturalistic colleagues responded to this? That is to say, the people that hold to chemical evolutionary theory. Generally, people have said this argument from DNA to design is going beyond science. It's violating the canons of the scientific method. But wait, I just showed you that we're using the same method that is used commonly in the historical sciences. Well, there's another rule that we didn't tell you about, they said, and that is the rule that says that you must infer only naturalistic explanations if you're a scientist. Okay? Now, so if you go back to that, our original, we call it the explanatory filter, showing chance, necessity, and design. This rule says you can't even consider design as a possible explanation. There's a fancy term for this canon of method. It's called the principle of methodological naturalism. You must, as a principle of method, if you're a good scientist, exclude intelligence as a possible explanation. Okay? So some people call that cooking the books, all right? And we have a way of illustrating this. Do we have the... Well, here's the explanatory filter again, and where the first node on the filter is to chance, the second to necessity, the third to design. Can we go back one? Did we skip there? No, I guess I'm missing a little. It's somewhat humorous if you're into this kind of thing. But the idea is that the naturalists are cutting off the third node, but not in all cases. Folks who are naturalistic in their philosophy, who say that matter and energy, that is to say nature is all that really exists, there is no God, will still allow inferences to design or to intelligence if the intelligence in question is a human intelligence. So archaeologists, anthropologists, even evolutionary anthropologists will infer intelligence in artifacts that they find. The rub comes in biology and also in cosmology. If you find evidence there of design prior to the advent of humans, you may be talking about intelligence that is divine, that comes from God. And it's in that case that we get pretty sticky about not inferring design, okay? That's when we say that we can't consider the possibility of an intelligent cause. What we're doing among those of us who call ourselves design theorists is that we're not only making the kind of case that I just made from evidence for design, but we're also challenging the rules of science that prohibit us to even exist. That would be a good thing for us to do, right? Because there are people who want to say it's against the rules to even talk about design. Hear no design, see no design. We have to, as good scientists, consider only chance and necessity or the combination. But what we're arguing instead is that that's not the way to go. That's not really the scientific approach. We need to look for the best explanation, not just the best naturalistic explanation. Okay? And there's a world of difference. If you limit yourself only to the best naturalistic explanation, then what you're really saying is that science isn't concerned about truth. It's not concerned about finding the best explanation, the best theory, no holds barred. It wants only those theories that conform to a set of preconceived philosophical ideas, namely that nature is all there is and there is no designer behind nature. Okay? So that's our general case. It has an empirical side, that is an evidential side, and also this challenge to the reigning philosophy of science. Now, as a special little capper to this talk, I want to show one more piece of video that I think, in case you're not persuaded of the evidence for design yet, I'd like you to see a little motor. This is, what you'll see as the video starts is a flagellum. This is a whip-like tail on the outside of a cell, and it functions as a propeller. And as you go inside this cell, you'll find that there is literally a rotary motor made of some 40 separate protein parts. And we're going to do, now, the animator's going to take us inside, and we're going to see that there's a rotor, and there's stators, and U-joints, and bushings, and these little proteins on the side here are going to peel away, and we're going to see the rotor on the inside. And this is animation, not of something that Mazda designed, but of a motor in low life, in a bacterial cell, in a prokaryote, one of the simplest forms of life on Earth. There's a sophisticated rotary motor. It's acid powered. It also there's a whole chemotaxis system that allows the motor to change directions and chase food, and it rotates at 17,000 RPMs and can turn on a quarter turn in reverse direction. Okay, so there's a very sophisticated machinery in a very simple form of life. And a scientist named Michael Behe, who's part of our intellectual movement, has written a book called Darwin's Black Box, and I'd highly recommend it for people who are interested in this kind of thing. Behe makes a very simple but compelling argument. He says systems like this, that are functionally integrated and require many separate parts working all at once, can't develop gradually. And he says the reason for that is that he uses a term he says they're irreducibly complex. And he uses an example of a mousetrap to illustrate this. With a mousetrap, you have 5 working parts. You have a platform, a lever, a catch, a spring, the hammer that does the killing part. And you need all 5 of those to actually catch mice. If you're missing the lever or the platform or the spring, Behe says, you don't catch 4/5 as many mice. You have a broken mousetrap, okay? And he says if you apply that to the kinds of irreducibly complex systems you see in the cell, you realize quickly that the Darwinian mechanism of natural selection acting on random variation could not produce those machines. And there's a very simple reason for that. Because the Darwinian mechanism is natural selection selects for functional advantage. If you lose a single part, you don't have any functional advantage. There's nothing there for natural selection to select. You take out one of those protein parts, you have a broken motor. You don't get 90% of the locomotion, you get 0, zip. Okay? So natural selection can't help you build a motor through 1 protein, 2 proteins, 3 proteins, incrementally in little parts, because you get no function until the very end. Okay? So what that means is it throws the whole thing back on chance alone, or else design. And Behe says, look, it's much too complex to have arisen by chance. If a single protein couldn't arise by chance, certainly a functionally integrated system of 40 proteins could not. And therefore, he says, given those 3 options, chance, natural selection acting on chance, and design, I say it's designed. In fact, he says, you know what? It looks designed. And therefore, I think it really is designed. So if it looks like a duck and quacks like a duck, it's a duck.